Here we're going to look at question 17 from section 2 of the ENGAA specimen paper. Now in this question we're given quite an old diagram, which is pretty tricky to draw to scale, where we have a cylinder with a radius of 2 meters, which is a centre which is given position O. Then we're then told the centre of this cylinder is a distance of 4 meters away from a point P, which is the point that a slab of mass 5 kilograms and length 4 meters meets a rough surface. So there is a normal force from our cylinder against our slab, which is occurring at this position S, and what the question asks us to then do is to find N, this normal force from the cylinder against our slab. Now if you'd like to have a go at doing this question yourself, then please pause the video now. Otherwise, let's have a go at doing it. So this question initially might look a little bit daunting, since we have absolutely loads of lengths and variables on here, which might all seem a bit odd and not necessarily related. But what we can do is let's try and break it down and see if we can work out why we're given this information. So I think the oddest bit of information which we're given is this distance from P to O. So this isn't the piece of information which you'd normally be given in a question like this, and looks a bit out of place in a question like this. So let's have a bit of a think about it. Now what we could really think, all this information really looks like it's going to be useful for, straight away, is that it makes a nice triangle like this. So here we have a radius going from O straight up to the point at which our normal force is acting. So once you realise this, you might be able to see why this is a bit more useful. Now I'm going to redraw this triangle just down here, and with our length of 4 meters and our radius of 2 meters labelled on. Now I've also put this is a right angle here at S. So this is just because it's a radius going to meet the point, or this slab, which is going to meet at a point directly across the surface of the cylinder. So it's definitely going to be a right angle, giving us this nice right angled triangle. So what can we work out from this? Well, as you see, I've labelled an angle on here, but what we could do first of all, which is a bit easier, is just use Pythagoras to work out the length of the triangle along here. So doing that, we find this length is 2√3 meters. Now why is this going to be useful? Well, it gives us the distance from P at the corner of this triangle right up to S. So the distance from this point P up to the point the normal force acts at. So while this might not initially look too useful, we can come to that in a moment and see if it is going to be, since all we're trying to do now is fill in as much of the diagram as we possibly can. Let's go back then and consider this angle in here, theta. So if we want, we can just use some basic trigonometry to try and find it. So we just know that sine theta is going to be the opposite, 2 meters divided by the hypotenuse of 4 meters, which of course is just a half, giving us an angle of 30 degrees. So that angle of 30 degrees is just labelled on here in our diagram. Now this seems to be all that we can really get from this triangle. So how about we rub some things off our diagram and see if we can make it a bit clearer what's actually happening here. Make it look a bit more like a conventional sort of question. Okay, so you can see that what I've done is I've removed our length of 4 meters from P over to O. We don't really need our radius at the moment, so I've taken that off. And what I've done actually is change our angle 30 degrees to 60 degrees. Now that's just because our angle is going to be double what it was before. And this can be seen quite easily by looking at the geometry of the situation. We have these two right-angled triangles which are identical and with an angle of 30 degrees each. So by labelling 60 degrees on here, we make this question look a bit more traditional. And hopefully it might sort of give you some ideas about about how we can actually solve it. So we have this point acting up here on our slab, which is acting perpendicular to the surface, and then we have a mass of our slab. So this, of course, we can label on as a weight, which is acting with a force of 5g downwards. Now this isn't too useful as it is, but what about if we resolve it? So by resolving it into different directions, we can pick the direction which is going to be perpendicular to the surface as well, along here, which is going to be given by 5g of cos 60 degrees, our angle that the slope is at. Now with this information, we have two different forces acting on our slab around our point P, which are both perpendicular to the surface. Now this might make you think of a topic, which is moments. So what we can try doing is taking moments around our point P. So first of all, we can look at one of the moments, or the moment of weight, which is going to be moving in the clockwise direction around our point P. So by taking the distance, which is going to be 2 metres, since the centre of mass of our slab is going to be right in the middle of it. Then we get the moment due to this weight is just 2 multiplied by this weight. Then doing the same thing for our normal force, N, which is a distance 2√3 metres away. Then we get that this magnitude of this moment is just 2√3 multiplied by N. So we've set these equal to each other because the system is just going to be in equilibrium here. But before we move on, one question which I might ask is, why have we taken moments around P? Why not about Q, or S, or any other position? Well, by doing about P, we've managed to neglect the fact that we're working on a rough surface. So this rough surface means that there's going to be a frictional force acting at this point P in either direction. Now, since we don't know anything about this frictional force, we don't know how rough the surface is or anything, we probably don't want to think about it too much. So by taking moments around P, then there's no distance from these forces to the point P, so therefore there's no moment, because the moment is just the distance multiplied by the force. So taking moments around P is actually making our life a lot easier and simpler. Anyway, with that in mind, we can move on and try and solve this equation. So, cos of 60 degrees, we know is just going to be a half, which of course is going to cancel with our 2 out the front, which is just going to make our equation a nice bit simpler, and we can divide by 2√3 to get that n is just equal to 5g over 2√3. Then we can just rationalise this by multiplying the top and bottom by √3 to get this answer of n equals 5√3g, all divided by 6, which is just what the question was asking us to do, and corresponds with answer B given in the question.